Hello everyone, welcome to the first video of TFHE handbook playlist. In this video, we will start this hopefully long-term series where we will cover this really good TFHE handbook from the practical perspective. So in this one, we will see the content table and the first introduction pages, and then we will cover the first topic of the handbook on morphology of TFHE ciphertexts. So let's start with the first page. Obviously, the name is TFHE a practical handbook, first edition. This work is being developed by the Zama team, and I must say this is a really good one, and I'm definitely recommending for those looking for any written resource on TFHE and also the TFHE implementation from the practical perspective rather than reading abstract papers. So let's see the content board. So this is the general overview. It's 120 pages around that. So in this one, we will see the introduction chapter and the first two subsections or subchapters of the second, one of the main chapters on the TFHE scheme. So, okay, let's see. Okay. Fully homomorphic encryption enables arbitrary computations on encrypted data without requiring decryption. This is obviously one of the most fundamental definitions of FHE. Obviously, I'm not going to read all the text, but I find useful that if we see the critical points or the insights to make easier to grasp the fundamental idea. So one of them is, I think, the final sentence of the first paragraph. The bootstrapping is an operation that informally refers to homomorphically evaluating the decryption circuit to remove one encryption layer while simultaneously adding another. This is one of the most crucial ideas behind the bootstrapping within the TFHE scheme. And hopefully in the upcoming videos, we will see how this bootstrapping process is done. One other thing I want to mention is, obviously we have ciphertexts containing noise, and bootstrapping is used during computation to allow more operations to be realized. This idea obviously applies to TFHE scheme as well. The good thing is, by using the LWE-based ciphertexts, TFHE supports the evaluation of small lookup tables via the so-called programmable bootstrapping or PBS operation. We will see these in more details in the upcoming videos as well. So let's see, what do we have? Yeah, of course, it's worth mentioning the definition of TFHE as well. TFHE is a Rust-based library developed by Zama that implements its variant of the TFHE scheme. And they mentioned that Zama's TFHE variant is designed to address some of the drawbacks coming along with the earlier versions. Particularly, it supports encrypted integer arithmetic for large integers such as U16, U32, U64, because the earlier versions were not capable of doing this. Okay, so this is a good illustration to make it easier to understand the ciphertext structure. We will see in more mathematical details in a couple of minutes. Okay. This is one of the first, I think, codes in the TFHE documentation. It simply imports a couple of things, and in the main function, we have a config variable, and we're setting client and server keys. This is a public setup. Server key is used for homomorphic operations, while client key, actually this is not a This may not be a public setup necessarily, because server key is used for homomorphic computations, where client key, actually server key is also used for encryption, right? Yeah. Client key is used for decryption, and obviously is never stored in the server side, which is obviously the strongest side of FHE. We have like 35 and 7. These are integers, U64 integers, and we're encrypting them using the client key. Yeah, this is a symmetric setup because we're gonna use client key for decryption as well. We're encrypting them using the client key and obviously taking their reference to avoid moving them. In the server side, we can add them, we can multiply them, and we can compare them, or some other operations as well, homomorphically without decrypting. And at the end, after the providing the result, client will be able to decrypt the resulting ciphertext and gonna have the corresponding plaintext to all those operations. Okay, the goal of the document is to understand the algorithms used in the TFHE scheme, introduce the integer arithmetic implemented in the TFHE library, and to provide all the necessary details to build a new backend for the TFHE library, for example, for a specific hardware, and then benchmark it against other backends. Okay, so let's start. TFHE scheme. As you may already know, there are several FHE schemes like BFE, BGV, CKKS, FHEW, TFHE, and maybe even more. Obviously, this document is completely focused on TFHE. So it's always good to start with the notation right here. So I'm also going to get my pen and try to illustrate them in a expanded mathematical way. So we're gonna work on the ring of integers, of obviously with a modulus q, and we're gonna denote it by z. Sorry, why am I not able to? Okay, zq, which is essentially equal to z mod qz. And we have another notation, RQ, which is actually a ring, and it represents the polynomial quotient ring, ZQX. Obviously, we have polynomial modulus x to the n plus 1. So let's start with this one. What does this mean? ZQX means actually is equal to the set of polynomials where, okay, let's see. Okay. A0, x0, which is 1 plus a1, x1 till, let's say, an xn. And the important thing is these AIs are going to be coming from this ZQ set. When add an additional this polynomial modulus, we're actually adding what we call negacyclic property, so that let's assume n is equal to 2, then our polynomial ring becomes x squared plus 1, and this means, let's say, let's suppose we have a polynomial of x squared plus 1. I'm just making it up, but this cannot be contained within the set, because by the definition of modulus, we need to take the mod of it and take the remainder as the correspondent element to this polynomial. So this is how simply polynomial quotient polynomial rings respect to modulus work. Okay, so also we will denote the elements of that Q by lowercase letters like small a. The elements of the ring gonna be given by uppercase letters such as capital A or uppercase A, and the coefficients of a polynomial a are given by these a0 to a n minus 1. Vectors are gonna be represented by bold letters. And if like that those vectors are vectors of elements in ZQ, then they're gonna be given by bold lowercase letters. But if they are vector of elements in the ring, they're gonna be given uppercase bold letters. We have rounding up, rounding down, and rounding to the nearest integer symbols. Also like the floor function, they have really different names, but they correspond to the same thing. So when we see this symbolism, it means dot product, as you see here. It's gonna be applied to both vectors and polynomials. We have uniform distribution, Gaussian distribution, and standard deviation stuff. Though we're not gonna concentrate on them, so I don't want to make this videos too mathematical, honestly, so I'm gonna avoid diving into them deeply. Okay, so LWE or learning with errors problems are lattice-based problems, and they're hard problems by the definition of cryptography. All the cryptographic systems relies on hard problems so that once you don't have the relevant, secret information, you're not gonna be able to reveal any hidden or encrypted info, obviously in a feasible manner. So the first definition of the handbook is the learning with errors definition. So we have a positive integer. We call it the LWE dimension. And we have Q, which is the ciphertext modulus. We have a vector S. Each elements are coming from the ZQ set, and this vector will be the element of the vector space ZQN. And we're gonna call it a secret or secret key, practically. And we're gonna sample all these SIs from a distribution D, so they're gonna be randomly sampled, and we're gonna call it a secret distribution. So we have another distribution, chi, and we're going to sample the error from this distribution, and we're gonna denote it by this E. Some resources use epsilon instead of E. That's okay. So they are essentially the same. So there are two versions of the LW problem. The first one is a decision one, and it implies the fact that distinguishing independent samples from LWE algorithm from the same amount of samples is going to be impossible. The search problem is actually to find the secret S where you're given an arbitrary polynomial number of samples from the LW distribution. So if this problem is, hard enough, then no one is gonna be able to, extract your secret out of the given public parameters. So the second definition is GLWE, or general learning with errors, where we're gonna be dealing with vector of polynomials. So in LWE setup, we had the secret being a vector of positive numbers from the ZQN vector space. In the GLW1, we have obviously the capital S, but I'm not sure if I'm going to able to write that, which is also a vector, but vector of polynomials instead. So this is going to be RQ to K. So, I mean, there's also needs to be written N, but I'm not going to write anymore. It's obviously the polynomial modulus. But this time, while, calculating it in LWE, we have a randomly sampled vector A, sorry, not capital, obviously, A times or dot S plus a noise will give the B. This is obviously a number because the output of this dot product will be a arbitrary number. Not arbitrary, but like just regular number, let's say. But in the GLWE setup, we're taking a dot product of two polynomial vectors and adding a polynomial noise. So at the end, we have another polynomial. Okay. The good thing worth mentioning is if we choose n is equal to 1, then this GLW distribution reduces to LW distribution. Because when we set the n is equal to 1, then this means here, let me find where. Okay, so like it was the polynomial modulus. When we set the n is equal to 1, then all the polynomials will reduce to the ordinary numbers from ZQ. Okay. Yeah, we have today's main topic, the morphology of ciphertext. So let me quickly refresh or like get to the new page, but I'm not able to do it. I don't know why. Okay. I mean, I'm not used to this, but it's a good practice though. Okay. The morphology of ciphertext, FHE ciphertext. So we don't have only LW or RLW in TFHE, but all of them are going to be based on LW. So let's start with LW ciphertext. Okay. So let Q in N be a positive integer, which we call the ciphertext modulus. Let N in N be a positive integer, which we call the LW dimension. So we already knew this. Given an encoded message, M tilde, let's say, and a secret key S in ZQN, an LW ciphertext of M tilde under the secret key S is defined as the tuple. So we have a encoded message from ZQ. So we're assuming here that we encode a plain text message into this ZQ element M tilde. We have the randomly sampled secret key from ZQ N. And we have another randomly sampled vector A from, again, ZQN. And we call it, maybe I shouldn't write there, but yeah. We call it mask of the ciphertext. And now, also, we have, the most important ingredient maybe, the noise from the Chi distribution. So we have message that we want to encrypt, and to do so, we sampled 3 random things: the secret key, the mask, and the noise. So to calculate it, ciphertext is a tuple where the first entry or entry of entries is the mask A, and the second one is B, which we call body. But how we, okay, A is randomly sampled. We have it, that's a public parameter. But how we're gonna know B? So B is calculated by this equation, A dot S plus M tilde plus E. And resulting number in ZQ will be equal to B. So this essentially is A0, A1 till A n minus 1, comma A dot S plus M tilde plus E. This is the LWE ciphertext. Of course, this is element of ZQ, but this time n plus 1 because we have an extra entry here. Okay. Let's see. Okay, so let's go for the GLW ciphertexts. Should I try to fit it into this page? Yeah, let me try. GLWE ciphertext. So the idea is the same, but like the mathematical structure is different. So instead of using the vector of numbers, so we're gonna use the vector of polynomials, just as I mentioned a couple of minutes before, maybe 5 minutes before, I don't know. Okay. So we have an encoded message M tilde again, but this time this is a polynomial. We have the randomly sampled secret key. This time a vector of polynomial RQ to K. We have random mask from RQ to K, and we have the this noise from again RQN, but from RQ, but it's obviously from a distribution. So the formula is again the same. CT, maybe I should write. Okay, CT is equal to a vector of polynomials, A0 polynomial, A1 till AK minus 1, and B, which is equal to A dot S plus M tilde plus epsilon. Right, and this is an element of the set RQ K plus 1. All right, I hope things are clear so far. And yeah, as I said, in the definition, the elements A0 to A n minus 1 are called mask, and the remaining element B is the body of the ciphertext. This is a really good thing, but I'm gonna mention about this later, because today is purely focused on the morphology of ciphertext. Also, it's even 24 minutes, which means I'm too slow. I don't want this video to be 40 minutes, so let's see. I'm passing all these private and public encryption. We will see in more details later in the upcoming sections. Yeah, here 2.4.3. So, and let's see the decryptions. Okay, new page. Okay, so we learned how to encrypt the encoded messages to ciphertexts, but obviously we need to know how to decrypt them as well. All right, so let's go for the GLW decryption. For decryption, we should be given a ciphertext, obviously, to decrypt, and also a secret key. And without the secret key, decryption shouldn't be possible. So we are given a secret key S. these are polynomial entities within the secret key, and we're gonna be given a ciphertext CT A0 till AK1 and B, where B is equal to A.S plus M tilde plus the noise. So we're given these A0, A1 till AK minus 1 and B, and also the secret key S1 to SK minus 1, and we're asked to find this M tilde. Obviously, we're kind of reverse engineering the encryption process, and obviously M, maybe not tilde, but yeah, M bar here. So M bar means the encoded message with noise should be equal to B minus A dot S, right? From this equation. So we're not given E, right? Because E is randomly sampled from the error distribution, so it's going to be random, even though like the underlying secret keys are the same for different ciphertexts. But we need to find a way to get rid of that noise at the end of the day. So this is essentially equal to M tilde plus E, the noise, and this is a ring element. Sorry. And this is the algorithm. So these are the things that we already discussed, and we're calculating. So wait, this is the encryption. Sorry. Okay, this is the decryption. So yeah, we're returning the M delta, and in the first, maybe not first, sorry, maybe in the last paper, it's called the phase. So like the encoded message with noise is called phase. We can call it or not, but I'm avoiding it for now just to make it more clear. And at the end, we're applying a sort of rounding algorithm. We will see in more details later. And at the end, after the sort of rounding algorithm, we have this M tilde. So that's why noise shouldn't exceed a certain threshold, because if it does, then the rounding algorithm will end up in a different ring element than the actual encoded message. That's why we need to control the noise, and that's why bootstrapping is really important in FHE. Another notion is trivial encryption. Trivial encryption means actually to encrypt with no randomness. So normally while encrypting, we have like the A0 to AK minus 1, we have the noise E, but in the trivial encryption, we encrypt with AIs are 0 and E is 0, and this actually is useful to convert any private setup into public setup by setting this encryption as the public key. It's gonna be useful later. Okay, we're coming into the tricky parts, because I mean, LW ciphertext and GLW ciphertext are relatively easier to understand because they're like vectors and they're polynomial vectors. But this lev, I don't exactly know how I should pronounce it, but I'm going to say lev or glev. I need to learn, but these are a bit different because their morphology is more complicated than the previous ones. So let's start with the low one, and the other will be actually another step forward. Okay, glev ciphertext or general lev ciphertext, I believe. Given a ciphertext modulus Q, a decomposition base B in N, and a decomposition level L in N, such that B to L divides Q, a glev ciphertext of a plaintext M from the ring under a GLW secret key S is defined as the following tuple of GLW ciphertext. So this CT bar is the glev ciphertext, but all these CT0 to CTL-1s are individual GLW ciphertext. So let's see in more details. So let's assume, and it's given by this formula Q over B to the J plus 1 times M. So for instance, for CT0, we have GLWE encryption of, obviously under the GLW secret key S, Q over B, right? Because in this case, J is 0, so 0 plus 1 is 1, and it means we have only B. Q over B times M, and this is an element of the polynomial vector space. So similarly, CT1, where J is 1, is equal to the GLWE encryption of under this S secret key S of Q over this time B squared, because J is 1 this time, 1 plus 1 is 2, times M, and similarly this is also element of the polynomial vector space. Actually, space of polynomial vectors, maybe, I don't know, I'm not sure. And at the end, CTL minus 1 is equal to the GLWE encryption under the secret key S of Q over B to the L, right? Because we're adding L minus 1 plus 1, so we have L times M, which is another element of our ring, or vector space, let's say. So then when we combine all of these stuff, we have a new ciphertext, glev ciphertext CT bar, which is actually equal to glev encryption of the message M, which is equal to these big vector of CT0, CT1 till CTL minus 1. And we can also write in a form where their entries are expanded, like GLWE S prime Q over BM GLWE S Q over B squared M, and it will go until the final element GLWE Q over B to the L times M. Okay, so I'm hoping that it's like it's more understandable now. But if you want, let's see in a representative shapes. So if we assume that normal learning with errors ciphertext look like this, these are all regular numbers, and GLWE ciphertexts are, these are each polynomials, and these are A, this is B, A, B, and in this case, how would glev ciphertext look like? This time, as it is the combination of different, not like a different GLW ciphertext, it would look like something like this, right? Okay, this is too big. Let's say these are the mask, and this is the body, and this is obviously one GLW ciphertext, so it will be L many. So we have a new layer for each GLW ciphertext. and this is obviously the final element of A, and this is the body. Maybe not. I mean, like, it's just to make it easier to understand. So we actually, we have a much larger dimension here in terms of mathematical standpoint. So, I mean, this was the intuition where I actually the first time understood like how these different ciphertext structures look like, and that's why I thought they named this section morphology of ciphertext. Okay, we have another. This is even more complicated, but like the idea is the same, so I think we will be able to understand it as well. Okay, it's called GSW or G in the more in the most generalized way, GGSW ciphertext. So we have another decomposition base B, another decomposition level L, so the same so far, and we have a plain text M, again the element of the same ring, and like the same setup continues, GLW secret key S, but this time this ciphertext is defined as follows: CT bar bar or CT double bar is equal to the vector of CT bars, and each CT bar is this time a GLEV ciphertext instead of being a GLW ciphertext. So the same idea, but this time CT0 bar will be equal to GLEV ciphertext of the Q over I mean, not obviously Q, sorry. I was confused with the earlier part. Minus S0 times M CT1 bar is equal to GLEV encryption of minus S1 times M, and at the end CTK bar will be equal to GLEV encryption of minus SK times M. So, but of course, in terms of polynomial moduli, this minus S, like this SK needs to be equal to 1, because like some minus 1 as it's rotating around the modulus. But the in terms of the visual stuff, not sure if I'm going to able to draw it, but let's try to make it. So remember that GLEV ciphertext look like something like this, right? And now we will have another dimensional layer. Like we're going to put, so this is a only one GLEV ciphertext. In the GGSW version, we're going to have many of these. So I'm going to try to do a trick here, even though I have no idea if that's going to work. Okay, this is copying, I believe. I don't know how to paste though. I'm not sure. Maybe Command V. I mean, not even close. Okay, so I'm just gonna try to do it once again. Copy and paste. I mean, I don't know how to paste here.Maybe one of these top bar bottoms. But yeah, I'm going to learn it next time. But you got the idea, right? So this is let's say only the CT0 bar. So we're going to have CT1 bar. Let me just remove this. We're going to have CT1 bar, CT2 bar, and until CTK bar, so that we will have many of these, and at the end our ciphertext dimension will be RQ, obviously, to, it was K plus 1, but this time we have a multiplier L, because we have L layers. So obviously it's not that easy to, maybe even impossible to visualize all the ciphertext, all the underlying polynomial coefficients as like random integers. It's impossible. But like in the upcoming sections, while we're seeing the the key switching stuff, the blind rotation stuff, we will be more able to understand the idea behind it, and I think it's going to be enough. So before ending the video, let's cover what we've seen so far. We've started with what the basic TFHE or FHE is, and what kind of ciphertext we're going to be dealing with within this playlist. It started with learning with errors, regular LWE. It was like the secret key, the masker, vectors of integers, or not integers, but some integers from some finite sets. And the generalized learning with errors, or general learning with errors, we had vector of polynomials. In G-lev ciphertext, we have the vector of GLW ciphertext. In GGSW ciphertext, we have the vector of GLF ciphertext. I hope it was both instructive, helpful, and fun. And I hope in the upcoming videos, all these abstract and maybe hard concepts will get together and will give you a intuitive meaning behind this fascinating field of cryptography. So I would love to, I would love to find out if you liked the video, if it was helpful, and if you have any sort of feedback, please let me know, and see you in the next video.